Yes, perfectly. Thank you. Go ahead.
Okay. Hello, everyone. I'm Master Sandoval, a PhD student from the University of Chile. The title of my presentation is a local particle in cell simulation of the magnetorotational instability stratified sub-relativistic accretion disk. The co-authors are Mario Riquelme from the University of Chile and Anatoly Spikovsky from Princeton University. So I'm going to start. Accretion disks are very common in astrophysics and essentially correspond to gas that rotates around a central gravitational object that will eventually fall onto the object, and the magnetorotational instability develop a turbulence that produces an efficient outward angular momentum transport, allowing the process of a gas accretion to occur. And in astrophysics, there are some examples of accretion disk, which includes a cataclysmic variable, active galactic nuclei, protostar, and X-ray binaries. So while we are interested in study the collisionless version of the MRI, that's because in very low luminosity accretion disk, where the accretion rate is much lower than the Eddington limit, the plasma thermalization time due to Coulomb collisions can be much larger than the time required by the plasma to be accreted onto the central object. Two examples of this kind of accretion disk are Sagittarius A star, the black hole at the center of our galaxy, and MHD7. Well, considering the case of Sagittarius A star, we can estimate the thermalization time for electrons, and so taking a volume of a plasma at 10 Churchill radius from this Sagittarius A star from the black hole, we can estimate the thermalization time for electron of roughly 10 years, while under the same situation, the time required for bioaccreting is roughly 1 hour. And also, if we consider that the thermalization time between protons and protons, of collision of protons and protons, and the collision between protons and the electron are much larger than the thermalization time of the electron and electron that I was estimated here, it means that all plasma or all the particles will not have enough time to thermalize during the time the plasma takes to be accreted. So we are in the presence of the effective collisionless plasma. The fact that the accreting plasma is collisionless means that several non-thermal plasma phenomena can take place. For example, the pressure anisotropy, different temperature between electrons and ions, and particle acceleration. All of these phenomena are inherently kinetics, and therefore study them requires a kinetic treatment. The acceleration has an important implication because it allows a better modeling of the broadband emission of systems like Sagittarius A star. We are also interested in study particle acceleration motivated by the gamma ray observation of the point source HES J1745, located close to Sagittarius A star. This emission, shown here as a blue, can be due to ions accelerated by Sagittarius A star, and also there are observations of diffuse gamma ray emission from the inner 100 parsecs around the Sagittarius A star, shown here in red, that also suggests the acceleration of particles by the central black holes up to the peta-electron volt energies. This suggests that the presence of some accelerations of ions close to Sagittarius A star, so we're interested in the importance of the MRI in the acceleration of particles. So what has been done? Well, previous studies of the MRI in the collisionless regime have considered, has been done using particle and cell simulations, where they consider a homogeneous plasma that correlates with a piece of the accretion disk. The plasma occurs in this point of view, acquires a shear-like velocity profile that develop the instability, and this instability produces a turbulent magnetic field as shown in this figure, and this is the responsible for the particle acceleration. In Kingolo, in 2018, shows that the collisionless MRI can develop a non-thermal particle distribution, that follows a power law distribution with a spectral index close to 2, which is consistent with previous studies of magnetic reconnection. However, to achieve this numerical convergence, they require very large boxes in order to develop the appropriate turbulence to produce a particle acceleration. But in realistic, the thickness cannot be increased indefinitely because the scale of height is given by the thermal velocity of the plasma divided by the orbital frequency. This means that the scale of height is roughly equal square root of beta times the lambda MRI, which is the most unstable MRI wavelength. This means that in the thickness of the disk contains a finite numbers of MRI wavelengths, where beta is the ratio between the plasma pressure divided by the plasma pressure. So we have it that in a realistic scenario, we cannot increase the size of the simulation indefinitely. So we are restricted to the domain of the simulation in the homogeneous scenario. So we focus on the study of the MRI using a particle cell simulation, including the finite value of the disk scale height by considering the effect of the disk stratification. This means that in our simulation, we include the vertical component of the gravity. We focus on the sub-relativistic regime, which is relevant for the accretion disk around black holes. And as our starting point, we consider paired plasma simulations where the electron and ions have the same mass, which is relevant for the dynamic of ions. And we start using two-dimensional simulations. We are also considering modest values for the magnetization, which is quantified between the ratio between the ion cyclotron frequency divided by the orbital frequency. We use magnetization values in the range between 7 and 20. We know that these values are much lower than realistic expected values, because for systems such as Sagittarius A star and MH87, these values range from 10 to the 8 and 10 to the 12. This means that one of our main goals is to determine the role played by the magnetization in the particle acceleration process. Well, in our current work, we run a stratified simulation, as I mentioned, considering open boundary condition at top and bottom, periodic condition horizontally, and we initialize our plasma with as an isothermal disk in hydrodynamical equilibrium, and with an external magnetic field in the vertical direction as shown by these black lines. We also consider the initial beta parameter of 100 in the midplane of the disk. And so if I put start, we can see that the instability is starting the linear regime from the center of the disk, and then it is propagated outward as the plasma is heated, and the disk thickness is increased. There is a zone of our simulation which corresponds to a corona-like component with a lower magnetic, lower particle density, a higher or relatively high magnetic energy contribution. In our simulation, the scale height of the disk is roughly the hydrostatic scale of height. And if we see it again, sorry, yes. After the linear stage, we see that the development of a turbulence and the formation of plasmoid, which is indicative of magnetic reconnection. The thickness of the disk grows, and eventually the size of the simulation is small for our thickness. However, we use boxes large enough that the situation is reached near the end of the simulation when the temperature has already reached nearly relativistic values. Okay, so to compare our result with the homogeneous scenario, we run a stratified simulation and unstratified simulation to compare the results. In both cases, in both simulation, the energy distribution acquires a non-thermal component described roughly by a power law. In the unstratified scenario, we reach spectral index close to 2.6, while in the stratified simulation, the power law index is harder with an spectral index close to 1.8. Then we include the effect of the magnetization. We see that the maximum energy reached by the particles is proportional to the magnetization. Here, as we increase our magnetization from 7 to 10, the highest energy of particles increase. This is consistent with this equation, where E and B are the electric and magnetic field, and L is the length scale of the magnetic field. However, the spectral index is fairly independent on the magnetization. So we are fine on, at least on this. Well, here I show the orbits of particles that are accelerated during the simulation. Here, during the simulation, at the beginning, the particles move freely close to the disk. They can move. When the instability is developed, the particles move closer to the current sheet and are accelerated when they move parallel to the current, along the current. Then after their energization, the particles keep their energy and, as you can see, remains trapped in the magnetic field, moving diffusively. Okay, so in conclusion, the stratification modifies the development of the MRI in several ways. It allows the expansion of the disk as the plasma gets heated. It allows the magnetic flux to abandon the disk. We can distinguish the disk plane from the corona, and the particle acceleration is more efficient than the unstratified scenario. In our next step, we want to run a three-dimensional simulation to explore the effect of using two-dimensional simulation. We also want the relaxed assumption of the ions and electrons having the same mass by using moderate values for their mass ratios. And we also want to make a thorough study of the effect of changing the initial beta parameter on development of the instability and the stratification. Thanks for your attention.